Day one of the normal and standard normal distributions and the empirical rule. Definitely the most important density curve in statistics is the normal curve, and it describes many types of data. The characteristic of the normal curve are its symmetric, single-peaked, and bell-shaped. It's completely described by its mean and standard deviation. The mean and median are the same and located at the center of this symmetric density curve, this distribution. Changing your mu, your mean, without changing the standard deviation sigma moves the curve horizontally, but it does not change the spread because you just said that you were keeping the standard deviation the same, and your standard deviation will control the spread. A higher standard deviation will mean a wider curve. A lower standard deviation will mean a narrower curve, but we'll find that this rule, the empirical rule, will fit any normal data, no matter how wide or how narrow it is. 68% of the data will lie within one standard deviation of the mean, 95% will lie within two standard deviations of the mean, and 99.7% of the data will lie within three standard deviations of the mean. By the way, questions about empirical rule, they do occur on the SAT exam, so this is valuable for that as well. 68, 95, 99.7. So here's my density curve. And I'm going to add labels to this density curve so that we can think about what the values would be. So the middle of my density curve would be the mean, and I think I will label it with a mu. And then the point of inflection, and what I mean by point of inflection is where when you're drawing a curve like this, and then you have to shift the way your muscles are moving to have the curve go like that, in between concave and convex. This is that point of inflection right here, this point where it comes together. And so here, right here, I can see the point of inflection, and it just so happens that that point of inflection will be one standard deviation out. And since I'm using mu, a population symbol, I will use mu minus sigma. So if I go one standard deviation down, I'm at that point of inflection, mu plus sigma. And then if I go two standard deviations away, so mu plus two standard deviations, then I'm at that 95% area, mu plus three standard deviations. Now remember, z-scores measured how many standard deviations away you were. So what z-score would you be if you were three standard deviations below the mean? You'd be at -3. And if you were at three standard deviations above the mean, you'd be at 3. So just below here, I'm going to put down here that my z-score here would be -3. My z-score here would be -2. This would be a z-score of -1. This would be a z equal to 0, z equal to 1, z equal to 2, and z equal to 3. All right, and then so those percentages. So within one standard deviation of the mean on both sides, if you can see this, that is 68% of your data. It's kind of hard to read that. Maybe I'll write black. So if I think of how the mean divides this in half, I have 34% on one side and 34% on the other. So that's using arithmetic. I divided it in two, split it to the two sides. Okay, from two standard deviations to two standard deviations, this will encompass 95% of your data will be in that window. And that, remember, we were thinking those are the not unusual values when you're within two. And so if you think about how this breaks down some more, if you have 95%, and remember you've got 68 in here, then outside of that, you would have, let's see, you've got 68 inside, so that would make this 13.5% in this little window, and 13.5%, because if you add 13.5 plus 34 plus 34 plus 13.5, you get 95%. And so that makes this half. This half is 47.5%. So all I'm doing is just sort of using that property of symmetry and breaking these into pieces and just dividing and adding and subtracting. Okay, so then outside of this, remember this is our unusual and our highly unusual past 3. This side would be half of 5%, so I can expect this to be 2.5% out on that side, 2.5% out on this side. And from 3 standard deviations right here all the way up to here, that was 99.7% of your data is in there. So if I want to break this down even further, I could think of this little green area out here as being a very small 0.15% of my data. This right here would be 2.35% of my data right inside there. And then the same thing balances on the top, 2.35%. And outside of it is 0.15%. So that kind of breaks that whole shape down. But then how do I use it? It won't be often that you'll get z-scores that exactly match up, but yeah. So let's look at this graph that I drew for the number of cats. You know, if you had this many cats, the number of cats that that Mrs. Hamby has owned. I don't know. I haven't had this many cats, but anyway, determine the mean and the standard deviation from this graph. So the mean will be in the middle. So my mean is 20 cats. My standard deviation, let's see if we can find the point of inflection. I see that looks like it to me. So the standard deviation will be the distance from the 20 to the 16. So my standard deviation will be 20 minus 16, which is 4 cats. Remember, standard deviation has the same units as the mean. And if you look on the other side, actually you can get the exact same number. Sometimes students accidentally tell me that they have 24 cats, but that's not the case. It's the distance. So how far is a 24 from a 20? That's 4 cats. Now, when I'm drawing these things, sometimes I can't make them look totally symmetrical, but I try my best. But if you show me where you have put your estimate of the inflection point, that will be helpful for me to be able to evaluate if you have done well. And here's your number of mini quizzes coming up. I would say the mean number of mini quizzes, 10 mini quizzes. Love these mini quizzes. But the standard deviation, how far away is that point of inflection from the mean? And it looks like it's around, this is at about 12, and this one is at about 8. So regardless of which side you pick, it looks like my standard deviation is equal to 2 mini quizzes. So you wouldn't be surprised if you saw 12 mini quizzes. And in fact, you wouldn't be surprised if you saw 14 mini quizzes, because that would be within 2 standard deviations of your mean. And we would expect 68% of the data would come between 8 and 12, but between 14 and 6, you'd expect 95% of the data. Okay, so now here's the thing. All models are wrong, but some of them are useful. So what am I saying here? Nothing in this world is going to be perfect. And as I keep saying in stats, you want to constantly be saying that you're not totally sure. And so when we are using this normal condition in order to solve our problems, since we know that no data is exactly normal, we will always use what's called the nearly normal condition. If we can show that it's normal enough, we'll use it. And so when we are testing raw data, we'll create a histogram, and that's in the next video. Well, in 2 videos. When we create a histogram, we're going to see if our data is unimodal, symmetric, free of outliers, and does our data fit the 68, 95, 99.7 rule. And if we can show that, we'll state that it's met the nearly normal condition. And if our data is from a distribution that's typically close to normal, like test scores done by many people, like the SATs, or repeated quantities of measurement, like a machine that's filling bottles at a factory, or biological characteristic like the heights of APStat students. If we have something like that, then it's probably reasonable that our data is meeting the nearly normal condition. And then, of course, we're going to work our magic, which we're going to find out how to do that. So, first of all, notation. How do we write probability? Okay, so to write probability, it looks a little bit like function notation. We've got our P here on the outside, and then this right here is going to say that we have a z-score that is between A and B. This next notation is saying that our z-score will be a greater than A, and this is a probability of that happening. And this is the probability of what's happening, a z-score less than A. So, and we're going to draw our curves every time. And I thought first I would just show you how to use the tables from the book because they'll be provided to you in the AP exam. And then after I show you how to use these tables, I'm never going to use them again because, you know, I just like to go with the easiest thing, and that would be my calculator. But we'll do a couple of these just so you can know how to use in case your calculator explodes during the test. You'll know how to pull out these tables. Okay, so these are already z-scores. Here's my z-score. What's the middle of a normal curve that has z-score? Standard means that it is a z-score curve. When they say standard normal, that means that they literally mean the middle of this curve will be 0 because that's the middle of a standardized curve. Okay, so we've got 1.33. I'm not going to, care too much about that point of inflection, even though that technically would be where the 1 would be. I'm not going to worry about that. Don't feel like you have to draw yours to scale. I want to be below a 1.33. So see how I'm shading that curve? Okay, so now let's go to our table and we're going to find, using the table, how to do this. Okay, this is exciting. Okay, here's my formulas for AP sheet. So the first page is some formulas. Then the second page, more formulas. Third page, aha! Tables for AP stats. There's a Z. Here's probability. And so now let's see if we can find this z-score that we had. It was 1.33. Well, these aren't helping me, being all negative numbers. Dang it. So I guess I'll go on to the next table. standard norm of probabilities. Now we have z-scores that are on the right side of 0. And let's see if we can find our 1.3. Whoops, you can't see that. 1.3. Now we go over. This is 1.30. See at the top. 1.31. 1.32. 1.33. So our first answer is the area to the left of z being 1.33 would be 0.9082. Okay, so let's write that down. Okay, so the probability of z less than 1.33 is approximately, I always like to put in a word of uncertainty. Whoops, hopefully I didn't pull up my speaker here. Okay. What was that thing? It was 0.9082. Okay, let's do the next one. Here's my graph. Here's my 0 in the middle. I need to be greater than a 0.7. I gotta be this side. Well, that's kind of interesting because that's not the way the table looks when you look at the table, is it? When you look at the table, going back to that exact same page that we were just looking at, okay, this table, I get the left side, but I want the area of the right side. So 0.7, 0.70, but that means that the left side is 0.7580. But remember, the area of any density curve has to equal 1. So if I take 1 and subtract the area that I do have, I will have the area of the other side. So let's write that down. So, okay, maybe I'll just keep that thing up. So if I go 1 minus 0.7580, I get 0.242. And now let's write a sentence. The probability of z greater than 0.7 is estimated to be 0.2420. Look how fresh and exciting I changed the wording. I kept it really fresh and exciting. All right, yeah, well, okay. Now let's see. Now let's do this next one. How would we do this next one with the tables? First I'm gonna draw it so I can visualize what I'm trying to do. This is 0, and I've got over here, I've got 2.15. Remember I said you don't really have to do things to scale. And then over here, it's probably closer to here though, negative 0.28. And I want the area between. Okay, so what I would say would be the thing to do would be if I could find this area. Okay, that would have been the area for the 2.15. If I could find that area and then subtract this area, then the difference would be what I'm actually interested in. So if I go to the table, going to the table, and I find the probability that my z will go below a 2.15 from the table, I'm going to let you look at your own table, I get 0.9842. And if I go to the table and I find the probability, and I have to go to the first table for this one to get the z being lower than a negative number, a negative 0.28, I get 0.3897. So when I subtract these two numbers, I get the probability that I'm between. So let me extend this page. So if I subtract these two numbers, I get 0.9842 minus 0.3897. That's going to be 0.5945. So my probability that my z goes, okay, well, I'm going to write it as a sentence. The probability that z is between negative 0.28 and 2.15 is 0.5945. Ooh, approximately. Or maybe I'll just say about here. There. Kept that uncertain. Okay, so that's the last time I'm ever going to use the tables, which you can use the tables if you like, but personally, I mean, because they are available to you during the test. But what I prefer to use is my calculator. And if we turn the page, we can see the calculator command. If you're in a college course, they'll probably allow you to write this command. I know they do over at UVM, but they do not allow you to write this calculator command on your AP test paper. You will lose points on the AP exam if you do this. So that, because you're going to lose points on the AP, then I'm going to take off a lot of points if you do this on my thing. So the only time you could write it on an AP test is if you defined every single variable as you were putting it in. But so let's just not do that because it would take too much time. So if you're using technology to find the area like we just did, then you would use this command. It's under second vars to access the distributions. And you would use normal CDF, left, right, mean and standard deviation. If you leave off the mean and standard deviation, it will assume that you have a standard normal. So if you do normal CDF, left and right, and you leave off the mean and the standard deviation, then it will assume that your mean was 0 and your standard deviation was 1. So that's standard normal. And if that's the case, that would need to be a z-score for the left and a z-score for the right. And then if you were trying to use this to get a z-score or get a value, there's the inverse command to normal CDF. The inverse of finding an area is finding those cutoff values, and that is again under distribution in your calculator, and it's called inverse normal, and you give the area to the left of the value and the mean and the standard deviation. Now in your calculators, the newest software, actually you can select area to the left, area to the right, or area in the middle. So you'll select what you want, but I'm kind of used to just doing the area to the left. So we're going to do those. I'm going to run through some examples, and this kind of ties into, in the textbook, they say, like, when you're solving one of these problems, you want to, for each problem, think through these steps. You want to state what you define your x variable, what you're trying to find, check those conditions, which we're going to spend more time on that, those conditions that you need to be true in order for this problem to even be valid, the most important being that it's nearly normal. Then you got to make a plan. You got to draw, label, and shade your density curve. then you need to standardize your X value or unstandardize your Z value, perform your calculations using technology, and then always write your answer in context and never sound certain. And I just want to say that when you're doing this, my cautions to you are to always draw your curves. Don't confuse those z-scores or x values with areas, because z-scores and x values are distance on the number line. Areas are the region in the density curve. Make sure you keep your left being your left and your right being your right. For example, top 10% would actually be a left of 0.90 and a right of 0.10. And z-scores to the left of the mean are negative, because remember, on your standardized curve, the middle is 0, and z-scores to the right of the mean are positive. So these are positive, those are negative. Okay, so here we go. SAT verbal test scores are normally distributed with, okay, when they give a capital N like that, that is code for saying that you have a nearly normal distribution. Actually, I'm going to capitalize my N for normal. And they are telling you that the first number will be the mean, and the second number will be the standard deviation. And SAT test scores don't really have units. But anyway, what proportion of SAT scores falls between 450 and 600? And then if 200 students take the test, how many students would you expect to be in this range? So we need to decide what kind of data we're working with. And I can see that I have quantitative data. I'm only saying that to remind you to think about what kind of data you have, because quantitative data is applicable for a density curve. Okay, so now for our conditions, the first condition that you're learning, besides being quantitative data, the condition that you are going to have to check in order to draw a normal curve, your data must be nearly normal. So the data is nearly normal. And how do you know that? Because it was given. See, I gave a reason why I know that. So now that I know that condition, I can actually draw my curve. And so I'm going to draw a nearly normal curve. And then I'm going to, I wish I could see the numbers and see the curve. But okay, I'm going to draw my nearly normal curve. The middle of my curve will be the mean. And my standard deviation. Okay, now I want my scores to be from 450. So that would be on the left of 500. I don't know how far over. You could drop more over if you want more room. Okay, and 600, I'll just drop more over. And I want to know the area. So I'm drawing, I'm labeling, and I'm shading. And now I need to find my z-scores. My z-score for the left side, which was the 400. Recall your formula for z-scores is x minus the mean divided by the standard deviation. So going to my 450 minus the mean divided by the standard deviation. My low z-score is negative 0.5. My z-score for the right is 600. It's 500 over 100. And that happens to be a nice, oh, not 2. Actually 1. A nice even 1. So I actually know the area of this right here is 34% because it's half of 68%. But that's just this right side from 0, like right here. But I don't know what this area is, so we're going to have to do this thing anyway. All right, so now I'm going to find the probability that my z is between a negative 0.5 and a 1. And I'm going to use my calculator to do that. And although I'm going to write it on here, I'm writing it in red because you wouldn't write it on your paper. I will put into my calculator, I would either type in normal CDF. Now, if I was going to work in the SAT world, I would say 450, 600, 500, 100. Or I could use because I have the z-scores, I can use z-score world. Negative 0.5, 1, 0, 1. And if I leave off the 0 and 1, the calculator will know it because 600 was a z-score of 1 and 450 was a z-score of negative 0.5. So that's really finding the exact same area. So let's do this with the calculator. Get my calculator. All right, calculator. Okay, well, oh, that's a histogram from another video. Okay, so second vars, see where vars is, to get to this distra. Can you even see that? Get that closer. Okay, normal CDF, second option down. We're never going to use the PDF, so ignore that one. Okay, lower, it says something really, really low, but I don't really want that. I want 450, 600. Mean is, wait, 500. Just looking at very, very nice. Anyway, 100. Paste. Must have been doing something kind of interesting. Okay, so that's the area point. So the probability of getting an SAT score between 450 and 600 is approximately 0.5328. Okay, let me just show you how the same answer would be achieved with my z-scores of negative 0.5, 1, 0, and 1. Paste it. See that same exact z-score, same exact probability from those z-scores. So this red stuff I didn't really write, pretend. And so then I will say that the probability of my z-score doing that is 0.5328. And then you've got to write your sentence because every time you do anything, you always write a sentence at the end. The proportion of SAT scores between 450 and 600 is estimated to be 0.5328. So then we have to make a prediction based on that, and if I multiply that value on my calculator, if I multiply that by 200, and then I'll want to keep at least one more data point than my original data. So when I multiply 0.5328 times 200, I get 106.0 6. So we estimate if 200 students take the test, approximately 106.6 students will be between 450 and 600. Or just in that score window. Well, kind of squeeze that in there. And if you are looking in this kind of problem, like check your conditions. We have 2, although eventually you can drop writing the quantitative condition, but right now we notice that it's quantitative. Nearly normal will be absolutely mandatory in order to draw that curve. Draw your curve, draw label shade, label your curve with numbers from the problem, show your formula for finding z-scores. What do I mean by that? I mean this right here. Right here, this is my work for finding the z-scores. Label your z-scores on the curve. That's a good idea. Write your probability notation. I like to write it with the z-scores since I've found them. You can, if you're going to use the x values, make sure this is an x. And write your probability as a decimal, write your answer in context. Complete sentences with units as needed. So, what if your college is only going to admit students with SAT verbal test scores in the top 10%? Well, we just proved that SAT scores, that we have quantitative data, and it is nearly normal. And because I wrote that it is nearly normal, and that was given, because I wrote that, it is appropriate to draw my curve. So I'm going to draw my curve, and I want, this was a mean 500, standard deviation of 100, and I want students who score in the top 10%, so 10%, which equals 0.1, and I don't know what this number is, but I do know that that area is 0.1, so I need to find out what that number is. So on my calculator, and this is kind of a little bit cheating, I'll show you the process that they're expecting you to kind of use, but what I do is I just go into my calculator and I ask the calculator if I do inverse normal for the area on this other side, what I do is I say, well, what would that z-score have been? And I ask the calculator, what's that z-score? So we'll ask the calculator, and then I say, calculator, while you're doing this work, why don't you tell me what it would have been in SAT world? And we'll get both of those numbers. So let me punch those in, and we'll get both of those numbers. And you can see that, and then I'll show you what they kind of think you're doing. I don't want to say that I'm cheating a little bit, but you know, I don't really like doing a lot of extra work. So, okay, so second distribution, inverse normal is right under normal CDF. And I say my area, see, this one will ask you about the area. I'm going to just do area 0.9 since I know that that's the area to the left. And I can paste. That's the z-score for being at the location that we are. And if I go back into distribution and I do this again, same area, but this time I tell it I want the mean of 500 and the standard deviation of 100. Paste that. And that would be the SAT score, 628.2. So I could write my sentence, but what they would have thought you would have done is they think you were taking your table, this table right here. And if you're trying to find the inverse for a 90% area, they're expecting you to have gone into the area section of the table, which is right here, and looking down in this area section of the table, do you see any numbers that look like 0.9? Right around, let's see here. Oh, here we go. These two numbers are the closest I see to 0.9. Which one is closer? This one here is 0.0003 off, and that's this one. And this one here is 0.0015 off. So this one is closest to 0.9000. This one's closest. So what does that mean? Like, let's go back to over here. You see that? Well, you can't even see that. Back to over here. That's 1.2. Go back to up here. Okay. 1.28. What did we get with the calculator? I'm turning this thing back on. Oh, look at that. 1.28155, blah, blah, blah. So they would have thought that you would have done this and gotten the 1.28, and then you would have had to use a little bit of algebra to get that. So let me show you how they would have done that. And in the homework, there's some problems like this. And, you can really highly expect to see a multiple choice that would have done that. So, so let's see, this number, now I got to get my calculator so I can remember what these numbers were. Okay, so we found that we got a 1.28, or 2 with rounding. And we found that we had 628.2 for an SAT score. What they would have thought you would have done is found this number, although probably not as precise, and you would have used this formula to find out what x is. So you would have taken your 1.28 from the table. You wouldn't have known what x was. You would have known that your mean is 500 and your standard deviation is 100, and you would have multiplied both sides by 100. And then after doing that, you would have added 500 to both sides, because you would have had 128 equals x minus 500. So then you would have said x equals 628. So it wouldn't have been quite as precise, but it would have done the job. All I'm asking from you is I would like you to write down this right here. You don't even need to solve it, but write down that right there. Just say that. So you'll write it like this. You'll write z equals 1.282. Then you'll write 1.282 equals x minus 500 over 100. X equals, and then from your calculator, you would have gotten this 6.82. So that way it avoids calculation errors if you just use the calculator to get the two numbers, but this being the work that you're writing out to support your answer. Seems kind of hokey, I know, but like, I like to get 5s and they want to see some work. But let's see, we checked our conditions, we drew our curve, we labeled our curve, we labeled, we never labeled the z-scores on our curve. There, and we never wrote a sentence either. So, yeah, see, show your z-score formula that you would use, quote unquote, to find your x value, and then answer this question in context. So I will write a sentence. To admit students in the top 10% of SATs, the college should use scores greater than 8 to 8.2 approximately.